Welcome to Lecture 2. Today, I'm going to be talking about the consolidation of Newton's achievement. Last time, at the end of Lecture 1, I mentioned that among the heroes of many Enlightenment figures were the natural philosophers of the 17th century. The names famous to us as authors of the scientific revolution of the 17th century: Galileo, Kepler, Descartes, Newton. These were also revered by the men and women of the Age of Reason, as the Enlightenment period is sometimes called. Among these names, that of Isaac Newton came to occupy a special position. By the end of the 18th century, Newton's stature had risen very high. His name was invoked in behalf of a new worldview, one incidentally that Newton himself would not have happily endorsed. I suspect most of you know at least a little bit about Isaac Newton. Albert Einstein is the most recognizable name from the history of science, but Newton's is not far behind. I'm interested today particularly in the impact Newton had on the 18th century. How did it come about that his star rose so high? That will be the question we want to focus on in this lecture. Let me begin with what Newton's achievement was. It centered around his book, Mathematical Principles of Natural Philosophy. That appeared in 1687 to great acclaim in Britain. Now, what had Newton done in the work that was so impressive to his countrymen? And also, how was it received across the English Channel on the continent? Eventually, the book came to be regarded as the basis for the new worldview I mentioned. We need to look into Newton's book to see what all the fuss was about. Let's start with what was in the work and why it was so impressive. Well, if you picked up the book and looked through it, the first thing you'd notice is that it was presented in the imposing format that the ancient Greek mathematician Euclid had used in his famous book on geometry. You know, the one we all learned in high school. Lots of definitions, propositions, corollaries, that kind of thing. It looked like a book on mathematics. Many of the problems and their proofs were very complicated. Newton had, in fact, invented a new mathematical technique, the calculus, to help him solve the difficult problems he was addressing. But he didn't use calculus in the book. He presented his conclusions in the traditional geometrical form of his day so that he'd be understood. Still, even then, not just anyone was going to be able to read this work. So you probably would have thought to yourself, this guy is clearly out of my league. I don't have the kind of mathematical skill it takes to even follow it. In situations like that, we usually realize that we're going to have to rely on what others say. Others, that is, who can read it. And those folks were indeed impressed. After all, Newton was claiming to present a system of the world by which he meant an explanation of why the heavens moved as they did. That's a rather bold undertaking. And what made it even more impressive was that his explanation of the motion of the heavenly bodies was cast as an application of a single general law that referred to all matter. Now, this was somewhat dangerous to do. The reason was that, historically, those people who appealed to matter and its properties to explain things ran the risk of being labeled materialists. That is, people who said you could explain everything through matter and motion. Historically, those folks had always had to defend themselves against the additional charge of being atheists, since they appeared to be using matter to explain things that others preferred to see as the result of God's actions. Well, Newton declared that all matter was attracted to all other matter by a special force. He claimed to know that the force depended on the size of matter and that it weakened as the distance between the pieces of matter got larger. It's called his inverse square law, because the force gets weaker in inverse proportion to the square of the distance. To avoid materialism, he held that the force was not intrinsic to matter. It had been imposed as a property onto matter by a spiritual activating agency. So matter was not sufficient by itself to account for the way the heavens moved. Spirit was also necessary in Newton's view, and that's an important point. Spirit has to be present in nature for Newton. And one place we see spirit is in the presence of the special attractive force that animates matter. Once the attractive force has been imposed on matter, it, along with some laws of motion he set down, was all you needed, according to Newton, to explain why the planets moved as they did. I think you can see from this that Newton was a very religious person. His religious views weren't of the orthodox variety. In fact, had he made them public, he could very well have gotten into trouble. But that doesn't mean that his own religious outlook was not important to him. It very much was. God played a central role in his system. One vital function God filled was to oversee the cosmos. Newton came to believe that comets represented a perturbing influence on the stability of the planetary system. They could be unpredictable, and their appearance introduced matter whose pull on other matter could upset the balance of the solar system. So Newton suggested God would set right any instabilities that developed in the system. For Newton, God was needed to supervise creation. The relationship between God and nature was an intimate one. Newton took seriously that verse in the New Testament of the Bible that declares God makes all things hang together. Newton had become convinced about the attractive force while working on the problem of the moon's motion. He had come to the conclusion that objects left to themselves would travel in straight lines at a constant speed. But that's not how the moon goes, so it must not be left to itself. Something must be pulling it away from its natural straight line motion into its orbit around the Earth, a kind of a cosmic string of some sort. But what? That's where the famous apple came in. When he was an old man, he told an acquaintance about a time when he was young and at home from the university. He was thinking about this moon problem. Why doesn't it fly off into natural straight line motion? He was in a garden and noticed an apple fall. And that's when it hit him. Not the apple. There's no evidence that the apple hit Newton. That's when the idea hit him. Maybe whatever made the apple fall extended all the way out to the orbit of the moon and made the moon fall. Maybe whatever made the apple fall was the cosmic string. Now, I want you to notice something in this. Newton didn't have to figure out the details behind why the apple fell, that is, what caused the apple to fall. In order to use this a new idea, he didn't have to say, here's what makes apples fall. All he needed was the fact that apples fall. Then he could say, whatever it is that makes apples fall also makes the moon fall. In his book, he explains why one can treat a satellite, like the moon, as a falling body. It's a special case, to be sure, and I don't want to get sidetracked on it, but the moon is falling toward the Earth without ever getting closer. Anyway, what he now did was to use the information he knew about falling bodies to think about the moon. Admittedly, he's out on a limb here. He's basing everything on the assumption that the force that makes apples fall also applies to the moon. But he pushed on and made some calculations based on this assumption. He knew how fast apples fall, and he could figure out, based on that and his inverse square law, how fast the apple would fall if it were way out at the distance of the moon. That would be the same rate as the moon would fall. Once he knew how fast the moon fell, he could calculate how far the moon fell in a given unit of time, say a minute. Now, whether you followed all that is not so important. If you remember this one point, his calculations are all based on an assumption that the same force that makes the apples fall also affects the moon. Based on this assumption, Newton was able to work out how far the moon should fall toward the Earth in 1 minute. He was then able to compare this figure with what he and others knew it to be from observation. His prediction was pretty close, but not close enough for the young Newton. So he put it away at the time. Maybe his assumption was wrong. Maybe the cosmic string was not supplied by whatever it is that makes apples fall. Newton didn't think his assumption was wrong, but it took a series of events between this youthful attempt at the moon problem and his book, 2 decades later, before he figured out why his earlier prediction was a bit off. In the book of 1687, it was complete. There, he was able to compare the distance he predicted that the moon fell in 1 minute, based on his assumption, to the value that a follower of Descartes had published it to be. And they matched beautifully. Well, how was all this received? In Britain, he won immediate fame. Once it became clear that all those propositions and lemmas made sense and were consistent, then people began to realize the power Newton's system had. And it didn't just apply to the heavens. You could use his law of gravitational attraction, and especially his laws of motion, to make calculations about the movement of masses here on Earth as well. What about outside Britain? Well, on the continent there were critics. The most important ones were among the followers of René Descartes. Earlier in the 17th century, Descartes had explained the motions of the heavens and everything else by rigidly separating reality into two realms, matter and mind. He avoided materialism by reserving for mind or spirit its own separate realm into which matter could not penetrate. He would not dream of trying to explain souls by appealing to matter. But by the same token, he would not bring spirit into the material realm. So for Descartes, spirit was not present in nature as it was for Newton. For Cartesians like the Dutchman Christian Huygens, Newton inappropriately mixed mind and matter when he allowed the force of attraction to be imposed onto matter. Attraction was a quality of mind, not matter. According to a Cartesian, there had to be an intervening material medium to transmit force. Force could only be transmitted, for a Cartesian, through the immediate contact of matter. Now, Newton had not identified any medium at all that carried the attractive force between, say, the Earth and the Moon. The Cartesians demanded to know how the force was transmitted. They interpreted Newton's omission of a material medium as a claim that there was no material medium. But there had to be a medium of some sort. For Cartesians, the idea that matter could attract other matter over space was saying that matter possessed the kind of hidden or occult force that Descartes had banished from natural philosophy in the first place. Why would Newton want to take us back into the Middle Ages? Over in Germany, the natural philosopher Gottfried Leibniz also criticized Newton's idea of attractive force in nature. His evaluation of Newton's philosophy came about in response to questions about it from the wife of the heir to the English throne. He had tutored her as a young girl when she was still in Germany. Now she was living in England, and she wrote her former instructor to ask his opinion of the new philosophy that was all the rage in England. Leibniz agreed with the Cartesians that Newton's failure to refer to an intervening material medium as the vehicle to transmit the attractive force was in effect a claim that the force acted as a hidden or occult power. If so, Newton resembled scholastic thinkers of the Middle Ages. Another of his comments was directed to Newton's belief that God's intervention was necessary to guarantee the system's stability, the business of the comets disturbing the system so that it would have to be put right again. Leibniz felt this demeaned God. He believed God supervised creation all right, but not by having to constantly correct it. Leibniz thought that God's control over nature was built in right from the start, so the system wouldn't need correcting from time to time. And he made his objection very clear to the princess. Well, that gives you some idea of what Newton's philosophy involved and how it was received when it appeared. We can see that there was plenty of controversy among the defenders of Newton, Descartes, and Leibniz as the old century ended and the new one got underway. But by the end of the 18th century, a so-called Newtonian view had become established among leading natural philosophers of the Enlightenment in France. And as we noted in Lecture 1, France was a real center of scientific activity in the 18th century. Incidentally, I say so-called Newtonian view because Newton's own insistence about spirit in nature didn't seem important to these French Newtonians. But for all that, they definitely saw themselves as Newtonian. How did that come about? What events led to the consolidation of Newton's achievement? Well, before Newton's philosophy could gain a foothold in France, it first had to come to the attention of the educated public there. That began happening in earnest after Newton died in 1727. The year before, a young Frenchman who wrote under the name Voltaire insulted a powerful nobleman in print. Voltaire had already served a stint in prison for things he'd written about the government. So now he was given a choice: go back to jail or exile. He chose the latter, and spent 3 years in England. In the early 1730s, he published his Philosophical Letters on the English Nation, a celebration of all things English, including its natural philosophy. For many French readers, it was their first taste of Newton's philosophy. What they read was that Newton was the destroyer of the Cartesian system. Voltaire went on to summarize what Newton had done, obviously giving it his endorsement over the system of his own countryman, Descartes. The heavily pro-English message of the book got Voltaire into trouble once more, and Paris was again unsafe for him. He took refuge in the independent province of Lorraine at the chateau of the Marquise du Châtelet, a friend he had recently met and with whom he collaborated until her death in 1749. The two of them worked together on the publication in 1738 of a book called Elements of the Philosophy of Newton, a more complete exposition of the Newtonian system than Voltaire's earlier work. And she completed a translation into French of Newton's Principia that appeared after her death. Madame du Châtelet aligned herself with the Newtonian Party, as the growing number of French defenders of Newton called themselves. But I have to point out, she was not a slavish follower of Newton. For example, she was sufficiently persuaded of the merits of Leibniz's outlook that she also published a book on his system in 1740. So Newton's work began to be known more widely in France in the 1730s. Some other specific events then occurred over the remainder of the century that added to its stature. I'm going to tell you about 4 of them. The first episode stemmed from a project that had been going on in France for some time. There was a long-standing undertaking in France to map the kingdom. As you can imagine, this involved taking detailed measurements of latitude and longitude. But when the surveyors correlated the degrees of longitude with the terrestrial lengths between distant points in France, they uncovered some discrepancies. The problem arose, apparently, because everyone had assumed that the Earth was spherically shaped. The leader of the project repeated the measurements to confirm their accuracy and announced to the Paris Academy in 1718 that the results meant that the Earth had a slightly elongated shape, kind of like an egg. Slightly. The problem was that both Christian Huygens, the defender of Descartes, and Isaac Newton had much earlier made calculations based on their different systems of mechanics that predicted a different shape. They said that the Earth should have a bulge slightly at the equator, more like a pear. Here were prominent members of the Cartesian and Newtonian camps agreeing that the shape of the Earth was flattened at the poles and bulging at the equator. So, the question back here in 1718 was whether to believe the predictions of natural philosophers or a claim that appeared to rest on careful measurement. And so the matter rested until the 1730s, when the French Academy sponsored 2 expeditions to determine whether the Earth was egg-shaped, as the measurements in France had suggested, or pear-shaped, as certain defenders of the philosophical systems of Newton and Descartes predicted. One expedition was to go north toward the pole, the other to the region of the equator. By taking careful measurements in these 2 places, it was felt that the question of whether the Earth was flattened at the pole or at the equator could be settled once and for all. Now, the leader of the expedition to Lapland, which left in 1736, was a 38-year-old mathematician and natural philosopher named Pierre-Louis Moreau de Maupertuis, son of a recently ennobled merchant. Maupertuis had gotten interested in this problem of the Earth's shape soon after it surfaced 2 decades earlier. He also was one of the first French natural philosophers to study Newton's work. He did that even before Voltaire brought attention to Newton's work. Anyway, he became convinced of Newton's system, and he turned into something of a crusader for it. But in so doing, he got a little carried away. You see, what happened was this. as I already noted, there was no necessary reason why the issue of the Earth's shape had to be regarded as a disagreement between the systems of Descartes and Newton, since there were partisans on both sides that made arguments for an Earth that was flattened at the poles. Nor did most of those arguing about the Earth's shape initially regard it as a test between these two rival systems. But Maupertuis, as I said, had taken on the role of a crusader for the Newtonian system. He recruited younger, impressionable academicians to his side, and he ridiculed Cartesians in the academy. Maupertuis reminds us that there is a very human side to natural science. His expedition returned much earlier than the one to the equator, and he brought with him findings that confirmed the Earth was pear-shaped. He then proceeded to exploit these results in defense of Newton, as if it had been a test between the system of Newton and of Descartes. Clearly, it was not all above board. Nevertheless, Newton's system gained a great deal, since many got the impression that his system had been confirmed by the expedition. That's one event. The second development that boosted Newton's reputation came by way of a challenge to his work that only ended up vindicating the Englishman's system. Here's how this episode unfolded. In the 1740s, one of the young men associated with the Newton party in France, Alexis Clairaut, was involved in trying to solve a tough problem. He, along with others, were trying to use Newton's system to resolve some irregularities in the moon's motion. They realized that the master himself had only taken into account the Earth and the moon when he tested his inverse square law. But the sun was also a huge body of mass. Surely it, too, along with the Earth, must affect the moon's motion. The problem was that applying the inverse square law to three interacting bodies was a horrendously difficult mathematical problem. In fact, Clairaut and the others soon realized that it was unsolvable. The best that could be done was to approximate a solution. As I mentioned, Clairaut wasn't alone in trying to work on this problem. Everyone agreed on the techniques of approximating the solution. But the moon was not observed to be where it was supposed to be, based on Clairaut's approximations. So, Clairaut announced to the French Academy on November 15, 1747, that based on his work, he had come to the conclusion that Newton's inverse square law had to be amended. He corrected the formula for the way gravitational force dropped off with distance, from 1 over the distance squared, as it was in Newton, to 1 over the distance squared plus 1 over the distance to the 4th power, 1 over r squared plus 1 over r to the 4th. This dramatic announcement stirred a pot already boiling over the merits and demerits of the Newtonian system. It wasn't long before Clairaut realized that he'd made an error in approximating the solution to the Earth-Moon-Sun problem. In the course of working through the complicated equations, he'd made a mathematical simplification that at the time seemed harmless. On closer inspection, it proved to make a big difference in the outcome. Clairaut realized that the others working on the problem had also employed the same simplifying assumption, and that this explained why they'd all pretty much agreed that the moon wasn't where it was supposed to be. When he corrected his mistake, however, the new approximation of the solution put the moon right where it was observed to be. There was no need to correct the inverse square law. Newton had been right all along. He should never have questioned the master. Okay, the third event that underscored the power of Newton's system took place in the late 1750s. It had to do with a comet that Newton's acquaintance, Edmund Halley, had observed back at the end of the 17th century. Halley had studied the records of earlier sightings of comets, and he claimed that the one he'd observed had a path similar to comets that had been sighted on 4 previous occasions, the earliest from 1456. So he realized that the comet he saw in 1682 had passed the Earth several times before. Assuming he was right, he calculated from the earlier sightings what the period of the comet was, around 75 years. And then he predicted that the comet would return again in another 75 years. That would be in the fall of 1757. Of course, Halley himself was dead when 1757 came. He died 15 years earlier. But astronomers knew about Halley's claim and about his prediction. Once again, it was Clairaut who took center stage. He realized that on this pass, the comet would travel closer to the planet Jupiter than on earlier journeys. So this time, it would be drawn a little out of its trajectory by Newton's famous force of gravitational attraction. So Clairaut went out on a limb and announced that the comet would be delayed. It wouldn't appear in the fall of 1757. It wouldn't be sighted until the spring of 1758. Well, sure enough, the fall of 1757 came and went, no comet. Then, in the spring of 1758, very close to the time Clairaut had identified, the comet named for Edmund Halley made its spectacular appearance. Clairaut's correction of the expected return was based on his knowledge of Newton's work. Without that knowledge, everyone would have been waiting in vain for the return of Halley's comet 6 months earlier. Clearly, this was a powerful system of natural philosophy. As the century began to draw to a close, Newton's system seemed to be acquiring almost godlike power. A final development that helped bring this about, and there were more than just these 4 I'm bringing to your attention, but this 4th one occurred just before the French Revolution in the late 1780s. Like the comet, this one too had its origin in Edmund Halley's rummaging around in ancient astronomical records. Back in 1693, Halley had read a paper to the Royal Society in which he noted that he'd been studying ancient records of lunar eclipses. He then said that he'd discovered if he ran the machinery of the heavens Newton had described backwards, the position the moon ended up in for the dates of the old eclipses was different from the one recorded for it in those historical records. Was Newton's system wrong? Halley didn't think so. He suggested that the orbit of the moon had been gradually shrinking toward the Earth. If that were true, then the old observations could be reconciled with the predictions of Newton's system. All that happened back in the 17th century. By the 1780s, the shrinkage in the moon's orbit was confirmed by others. That solved the discrepancy, but it introduced another big problem at the same time. Was the Newtonian cosmos unstable? If the moon's orbit was shrinking toward the Earth, it would someday collapse into it. Would the solar system collapse someday too? A brilliant young Frenchman named Pierre Laplace came to the rescue. He was able to show that the gravitational attraction and interaction of the Earth with the sun and the planets introduced a long-term perturbational effect that caused the moon's orbit to shrink gradually. But that same interaction would cause it to expand later. The moon's orbit underwent an oscillation in and out, one cycle of which took thousands of years. The Earth-Moon system was stable after all. And so, presumably, was the rest of the cosmos, Newton's system explained. Laplace used Newtonian principles to describe a stable world machine that appeared to run eternally. A decade later, this same young French devotee of Newtonian celestial mechanics wrote a book with the bold title, System of the World. In it, he made it clear that he had no use for Newton's belief that God would intervene to set the cosmos right when it began to get out of whack. We saw earlier that Newton had concluded that comets introduced pulls and tugs on planetary motions that would easily lead to instabilities. Newton felt that God would correct any developing instabilities because God was constantly present. One scholar has called Newton's God a cosmic plumber, fixing the leaks whenever they cropped up. To Laplace, this idea of Newton's was what he called a vain hypothesis. Laplace didn't need that kind of hypothesis to guarantee the stability of the solar system. It was stable by itself from the start. Clearly, Newton would not endorse the worldview of Laplace. He would not have approved of removing God from nature and letting it run by itself. But that's just what Laplace was doing. And he believed he was just working out the implications of Newton's mechanical system. Laplace's attitude here is indicative of a new worldview that wasn't restricted just to the physical sciences. It crops up in other parts of natural philosophy over and over in the 18th century. It's a worldview that some have called deism, which refers to the belief in a particular kind of God, one that created a world that runs by itself without the need of divine or direct superintendence. It came about when natural philosophers began to assert that nature was more subject to law. The more pervasive those laws were, the less was left to supervise. Now, I want to emphasize that not all natural philosophers of the 18th century were deists. And it's also important to realize that deists like Laplace were definitely not atheists. They believed in God. Sometimes it was a less personal God than Newton's God, but a supernatural power was necessary, all the same, to have gotten things started. Many deists believed that their discoveries confirmed God's existence, just like Newton believed his system pointed to a creator. Well, I suppose from our privileged standpoint, we can see how deism opened up an option that would figure prominently in the history of science. I find it fascinating that if some adopted Newton's physics without Newton's God, others have kept Newton's God. We'll continue to explore these themes as we go. We'll see, for example, that just as natural philosophers subjected the heavens to the rule of natural law, so too did they scrutinize the earth and its past with the same intent. And that's what we'll do in the next lecture.